Okay, so we already went over the 4 basic traversal algorithms: pre-order, in-order, post-order, and BFS. And I wanted to, note a few things on those. An in-order traversal. Remember that the difference is that when you process the route. So with a pre-order traversal, it's route, then you go left, then you go right. With an in-order traversal, it's going to be left, then route, then right. And then with a post-order traversal, you go with a left, then route, then right. Right. Each one of these has its own applications. For example, a pre-order traversal, it's the simplest, and easiest to implement, right, with a stack. And so if you just need to explore the tree, you don't care what order you process stuff in, then go ahead and use that. An in-order traversal comes into play for binary search trees. Binary search trees, if you've got a binary search tree, then in-order provides a sorted order. An in-order, right? That's why we call it in-order traversals. And a post-order traversal comes into play if you're trying to delete a tree, so tree deletion. Right? And you want to do this so that you delete the left subtree first, then the right subtree, and only after you've deleted those two things should you delete the root node. If you did it in a pre-order manner, if you deleted the node, well, then you would lose your references to the left and the right tree, and you would end up, not being able to delete anything. Right? And BFS has its own applications. Each one has a recursive solution, right? Including BFS, but we're not looking at that, right? So how, right? So how would you go about doing this? Let me come over here and let's go ahead and implement. Let's go ahead and implement pre-order traversal first, not as a list, but not as a list, but we'll just output stuff, right? So a pre-order traversal that is recursive. I'll go ahead and go rec here for recursive, okay? So I'm going to modify this a little bit to give it a tree node, right? And I'm going to call that tree node the current tree node, okay? Now, a pre-order traversal is going to process the node first, so let's do that. And by process, I just simply mean output it, printf, current dot get element, there we go, all right, and get rid of that, there. And then maybe print it nicely with a comma at the end, there we go. And then I don't want to print it on a line, I'll just print it out. So one process the node. And for that, again, for us, it just means printing it out. What do I do next with a pre-order traversal? Where am I going to go next? To the left subtree, right? So do we have a function to do that? Yes, this one right here, right? So current dot get left child, right? Okay. Where do we go next? After that's been executed, we return back from that recursive call. Where do we go next? To the right child. Right? Simple, right? Except that you also have to do with recursion, you have to do what first? Base case. All right? Base case. So if I've fallen off the edge of the tree, the current node has a null value. So let's detect that if current is equal to null. There's really nothing to do, right? If it's not equal to null, then we can, of course, print it out and then go to the left child, right child. But once we've fallen off the edge of the tree, we don't do anything. We just simply return. Okay? Let me change this. Since we're just printing it out, it should be a void function anyway. All right, there we go. Okay. All right. So let's come over here to the demo and see if we can now do it. Right? Remember that we were doing a pre-order traversal up here and printing it out, and then we're doing it again in our enhanced for loop. So we should have a pretty good information on what this looks like. So system.out.println in pre-order is going to look like tree.preorder traversal recursively. Except that, where do I start? Where do I get the whole thing kicked off? At the root. So tree.root. That requires me to break encapsulation, right? If I did it this way, it would be a leaky abstraction because I'm forcing you to break it open, pull out the root, then just to give it back to me so that I can, the tree here, so I can do my pre-order traversal. Nope. We're going to have two versions of this stuff. And this is what you usually, the way the pattern usually works in recursive algorithms. You get everything started by a non-recursive version of it. And then you hand off the recursive version here, I'll call this dot pre-order traversal of this dot root, right? And I get the whole process started here by invoking this over here. Rec, thank you. All right. Okay. And now over here, it's no longer leaky abstraction. I don't have to provide anything. You take care of it, tree. It's your root. You should know how to do it. Let's go ahead and see if it works. ABDGL blah 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 blah. ABDGL blah 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 blah. Looks like it works to me, right? All right. That's pre-order traversal. What would post-order traversal look like? Let's go ahead and copy and paste everything. An in-order traversal, let's say. Okay. In-order traversal recursive. In-order traversal recursive. If I've fallen off the edge of the tree, I don't do anything. Otherwise, when do I process the node now? Before or after I go left? After. So just move that one line down. And make sure, of course, that you're calling the correct functions. Right? Let's see if that works. We never did, I guess we did on paper or electronic paper here. I don't know what it was, but it's okay. I'm pretty confident that this will indeed be a in-order traversal. In-order traversal. That looks about right. Here's the sniff test. Where is A? It's in the middle, right? What if I were to do the same thing but for a post-order traversal? Post-order traversal. Post-order traversal. Recursive. Once again, I'm going to do a copy pasta. Right. Don't want to do this in general, but okay. Post-order traversal. Call post-order traversal, post-order traversal, post-order traversal, post-order traversal. But when do I process the element now? At the end. Let's run it and see if A is at the end. It is indeed. Right? So there's my post-order traversal. You can clean up the output if you want to, but I don't care. Right? All right, so each one of them has a recursive solution. Right? You simply change when you process it. Before, middle, or after recursing. Cool. So does that mean that I've changed my mind and recursion is now awesome? No. This is still better because you're not abusing the call stack. This is doing the exact same thing. This is the tree walk algorithm that we looked at last time. Or here's the stack-based post-order traversal, where distinguishing, is this the first time I've come into you, the second time I've come into you, or the third time that I've come into you in order to process it, right? This is the third time that we've come into it, so let's go ahead and process it because it's post-order, right? This is still far better because you're not abusing the call stack. If you have a very deep tree, millions of nodes, right, then this is not going to be possible over here at all, right? Okay. All right, so, but it's a quick and dirty way of doing it. All right, so you should still prefer, prefer in-memory stacks. Don't abuse the call stack. Right? Small and defenseless. Right? We also looked at breadth first search. I should have put that up there too. Right? Breadth first search, BFS, top to bottom, left to right. Right? It uses a queue to do its job, right? But otherwise, nearly exact same code as pre-order. In fact, we can take a look at it again here. There's the pre-order traversal where we establish a stack. We push the root while the stack is not empty. We pop whatever's on top, process it, push right, push left. BFS is exactly the same, except we have a queue. We enqueue the root while the queue is not empty. We pull off whatever's next in the queue, process it, and then push left and then right. And so all we're doing is changing the data structure and the order of those two things. This goes back to, again, one of the themes of this course, that smart data structures and dumb code are a lot better than the other way around. This is dumb code. Put stuff in, take stuff out. Put stuff in, take stuff out. Right? It's the choice of data structure here that's giving you completely different behavior with completely different applications. Right? What about the efficiency of all of these? right? So each one of what we already talked about, a few applications. But what about efficiency? Each one is designed or intended to process every node exactly once, right? So nodes are only processed once, right? Nodes may be visited up to 3 times, but only processed once. We're not going to reprocess it. We process it once when we come into it, if it's pre-order, once when the second time, if we're doing in order, and once on the third time if it's post-order. As a consequence, all of them are order n, right? Because there are n nodes, right? N nodes and n minus 1 edges, right? So if you want to look at it with respect to the edges, that you traverse this edge so many times, it's the same thing because it's a tree and it's sparse, and the number of nodes is equal to the number of edges minus 1, right? So if you even if you considered that a traversal was your elementary operation rather than the processing, it's still going to be order n, right? Because it's going to be 3n instead. But we've still fallen short, right? Our original goal, remember, was to have efficient operations for searching, retrieving, insertion, and deletion, right? And we're not there yet. Come on, don't go to sleep. There we go. There. All right. Let's go with this binary tree again. I think last time we searched for R. If we had done a BFS, we would have done it and gotten very unlucky because it's the last one there, right? If we had done a pre-order traversal, we still would have wasted time over here. And suppose that this wasn't the only thing hanging off of L. Suppose that there were 1 million elements over here. We would have ended up looking at 1 million elements before coming back up here to check to see R is here, right? Likewise, with in order, post order, it doesn't matter, right? It's no better than linear search because it's order n. Yes, you could get lucky. I search for B and I only make 2 comparisons to find it, right? But you can't look at the best case scenario. The worst case scenario is you find the thing that you're looking for at the very last place, right? In which case you've done 1 million or n operations, okay? So to solve this, we need more structure, right? And that's going to be binary search trees. Generally, what we're going to be doing is we're going to be storing elements in a tree, right? And we can also impose additional structure on that data, that it be ordered in some way, right? Binary search trees do this for us. Binary search trees keep track of what's called a key. And we understand keys from databases, right? In fact, this is going to be a surrogate key, a key that is unique, right? So we're going to put additional structures and restrictions on this. For simplicity, our keys will all be integers. That's actually how it's done in practice too. Right? You remember we briefly talked about equals and hash code. What does a hash code do? It takes the state of an object and boils it down to one number, one integer, right? So for simplicity, our keys will be integers. That's an easy simplicity because that's how it's done in practice, using hash codes. And our keys, all our keys will be unique, right? What if it's not unique? You can always find a tiebreaker. You can always find a tiebreaker, right? Suppose that you have an invoice. They purchased exactly the same number of items, exactly the same number, actual items. Both of them had the same equipment. It cost the same. They somehow did it exactly on the same date. How could you still distinguish between these two invoices? They had the same customers, same for some reason, right? Everything was absolutely the same. How could you still break that tie? Okay, it had the same salesperson too, right? The entire state of the object was the same, but you still needed to distinguish between these two things. What's the default? How are things distinguished? How does the dot equals method work in Java? Based on the memory address, right? You will always have a tiebreaker, a memory address, a surrogate database key, right? That's actually what you should probably do, a database key, because that's why we did surrogate keys, the keys that were auto-generated, not the natural keys like UUIDs, right? There's always going to be a way to break a tie. So this uniqueness constraint is not that big of a deal. The data for demonstration, the key and the data will be the same, right? In other words, when I write out a tree, I'm just going to use a bunch of integers, right? If those are invoices, fine. But in practice, if they're invoices, that's fine. But we're only going to use integers here. All right, so here's the binary search tree property. So binary search tree property, right? For every node that has a key value k, all nodes in its left subtree are going to be less than that k. All nodes in the right subtree are going to be greater than that k, right? So just visually here, what do we mean? Well, we're going to have a node here, and its key is k. Everything in the right subtree over here is going to be less than k. Everything over here in the, left subtree, right subtree, I keep screwing that up. Everything over here in the right subtree is going to have a key value that's greater than k. And remember that we're doing uniqueness. Another way of relaxing that uniqueness requirement is to just simply break ties to the left or break ties to the right. It doesn't matter, right? But for us, we're going to keep them all unique, okay? Let's take a look at our first example. Binary search tree, all right? Now let's verify this. 50 is the root. Everything over here, is it less than 50? Yes. Everything over here, is it greater than 50? Yes. Look at any other node. For example, 20. Everything in its left subtree, is it less than 20? Yes. Everything in its right subtree, is it greater than 20? Yes. In other words, it holds for every node. For every node in the tree with key value k. Things in the left subtree are less than k. Things in the right subtree are greater than k. Okay? Why does this help us? Well, what are the basic operations again? What are the, let's go with basic operations. CRUD, right? So let's do searching. Right? Where are we going to start, first of all? Same thing that we've been doing this entire time. You start at the root, right? Then what are we going to do? In fact, let's just do an example over here. Let's search for 45, right? So I'm going to start at the root here, 50. Should I even bother looking at the right subtree? Absolutely not, because 45 is less than 50. Right? So if it exists, where is it going to be? In the right subtree. How many comparisons did I make to do that? Just one. Now, granted, is it equal, or is it strictly less than, or is it strictly greater than? That's technically two comparisons, but ultimately this is going to be a comparator call, right? So it's only one comparison that we're going to do this, just like binary search. Right? All right, now we're at 40. I already compared 50. Now I'm going to compare 40. 42 is greater than 40, so where do I go? Right. All right. 45, that's equal to 45, and we're done. I made 1, 2, 3 comparisons here. So 3 comps. All right? And it was a successful search. All right? Let's search for 28. No, let's search for 12. Search for 12. All right? So we're going to compare it to 50. All right? There's one comparison. Realize that we need to go left. We're going to compare to 40. There's 2 comparisons. We realize that we need to go left. 3 comparisons when we compare it to 20, and realize that we need to go left again. Right? 4 comparisons to compare it to 10 to realize that where do we need to go now? Right? And 15, that's the 5th comparison to realize that we need to go left. And 12 to see that it's equal, and we did 6 comparisons, 6 comps. Okay? All right, we go left, right, depending on which direction it sends us in. Let's search for 42. First of all, is 42 in there? No, you can have unsuccessful searches. How many comparisons does it take to get me there? 1, 2, 3, and then realize that there's where it should be, 42, but it's not there. So 1, 2, 3 comparisons. What is the maximum number of comparisons that I'm going to have to make to search for anything in this tree? The depth, right? What was the depth of this tree, by the way? 12 is the deepest, so it's 1, 2, 3, 4, 5, right? So the maximum number of comparisons, comps, is going to be D plus 1. Why is that plus 1? Well, it's the last one to see that is that the thing I'm looking for, right? I remember that the depth was 1, 2, 3, 4, 5, and it took us 6 comparisons there, so that jives. This is at most D plus 1, which is going to be order D. Remember that was our goal. If we can get operations that are proportional to the depth, and we can guarantee the depth is going to be logarithmic, then we've won, right? We've found our data structure. So you start at the root, right? You make comparisons to go left or right until you find what you are looking for, right? The complexity here is at most D plus 1 comparisons, which is order D. Right? Now, we don't have a guarantee that the depth is going to be logarithmic. We need something else for that goes beyond this course. But if we can get that, then we could have log n. Right? There's no guarantee that it's log n, but it could degenerate, right? Because like it's a linked list, and it's no better than linear search through a linked list. Okay. Now, before we go on to the other two, I want to start designing this thing. Okay. I immediately jumped to object-oriented programming. A binary search tree is a binary tree, right? So what if I were to, say, create a new class, binary search tree, of elements of type T, and I extend a binary tree of elements of type T. Is a binary search tree always a tree? Yes. I agree to that it belongs in that kind of hierarchy. But as a consequence of that, we start inheriting stuff. Does everything that we inherit make sense? Does a pre-order traversal on a binary search tree make sense? No. An in-order traversal might make sense because that'll give you the ordering, right? Does a post-order traversal make sense? No. Right? Not only that, but all of these are public methods, right? I should have made that private, by the way. I should have made that private. I should have made that one private, and I should have made that one private. Otherwise, they're leaky abstractions, right? I only allow public access to the entry point and not to the thing that requires you to give me a tree node. Right? What else do we have? Does a BFS traversal make much sense? Maybe, maybe not. I mean, what does a BFS on this give you? Let's go ahead and get rid of all that. There we go. What does a BFS give you? 50, 40, 60, 20, 45, 90? Is that helpful at all? I don't think so. So let's start fresh, right? It might make sense from the standpoint that all directors are people, but we already saw that doesn't make sense in general when you've got a person that is a director and an author, right? So, no. Right? You could use a composition over inheritance instead. I could own a binary tree, right? I could say private binary tree T underlying tree. It's not going to allow me to do any of the things that I want to do now, though, where I'm inserting stuff and retrieving stuff and doing this binary search on it. All right. So I'm not going to do that either. Instead, I'm going to say, okay, fine. We'll just go ahead and have a root, just like we did with the other one. Maybe you also want to keep track of the size. Keep track of the size. Right? I'm not going to do that just yet, though. All right. All right. So binary tree. Let's go ahead and have a public binary tree constructor. This dot root is equal to null. we might think of something more clever later on. Right? All right, so how am I going to get stuff into my tree, first of all? Let's design that. Let's go ahead and forget about our binary tree. Forget about this demo here. I need a basic CRUD. 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 Right? I don't know what that would stand for, but I don't know. Why didn't they do that? Yeah, I guess CRUD sounds better. Like it's garbage. Just get it done, right? So CRUD. I need a way to insert elements. I need a way to retrieve elements. That's what we just covered. Elements. I need a way to delete elements. Right? Okay, and then update is basically the same. You just delete it and then you insert it again. Right? We've really only talked about how to retrieve these things. We just talked about how to do this, right? You search left or right to find what you're looking for. But that doesn't stop us from designing the interface, because the interface doesn't actually need an implementation yet. Right? I need a way to insert stuff. Public, void, add an element of type T. Right? Okay, because it is generic. So we're going to add that element type T. Right? And then to do implement. There we go. All right. What about a way to retrieve elements? Right? So public T, find or search for elements of type T. Right? It sounds kind of weird at first because, well, you have it. You give me X, I'm going to give you X back. Remember, it's a key. This ends up being a key, right? So whatever the key is, whatever type the key is, and then we actually give you the data. So you'd give me a key to, like, the primary key for an invoice, and I would give you the invoice back, right? But we're keeping this simple, and we're just going to go ahead and go with type T. Yes, you gave me 10, and I give you 10 back. It seems kind of stupid, right? But how are we going to do this? Right? Let's come back to it. Delete elements. Right? Public T, delete. Elements of type T. Now, why am I returning this? Remember how we designed this with our list data structure? Right? You want to remove the element. I'll go ahead and remove it, but also give it back to you. Right? I want to remove the element at the ith index. Here you go. Right? I'll remove it and give it back to you. For now, let's return null to make sure that this compiles. All right. Let's just take care of the first step. Is it the root? This dot root, is that equals X? Right? How do I begin answering that question? I could do something like this. If this dot root dot equals X, then return this dot root dot get element. Actually, the element, right? Dot get element equals X, right? But now, where do I go? Otherwise, else if it is less, go left. Else if it is greater, go right. Does dot equals answer that question for me? No. Okay. How are we going to answer this question? How are we even going to begin to answer this question? Compare to? Compare to. That assumes that it's comparable. Is T comparable? I don't know. I don't know anything about T. I just know that it's an object. That's why I was able to do equals before, right? Okay. What other tool can we use to make it so that we can compare elements of type T? We could use the hash code, but then if it's based on memory or just some hash function, that doesn't tell me that that invoice is greater than that invoice in total, or that that invoice is greater than that invoice because the salesperson's name comes first, right? What is that thing? How do we compare things in Java? Comparator. So let's give this thing a comparator. For elements of type T, CMP. Comparator. A CMP is good enough. Now what I'm going to do is I'm going to require you to give that to me because I don't know anything about T's. Right? You know something about T's because you're creating a data structure to hold them, right? Let's go ahead and import this so that it is quiet. This .cmp is equal to CMP. Right? If it were naturally orderable, right? If it had a compare to method, it was comparable, then I wouldn't have to use this comparator. Right? But then I would have to have a bunch of if-else if statements. If t is comparable, right, then go ahead and use the compare to method, right? How do I do that? If t instance of comparable. I'd have to do something like that. Gross. Right? But that's how it's done in practice too. Right? I want to keep this simple. All right, you gave me a comparator. How do I answer this question now? The comparator. This.cmp.compare the root and x. And if that's 0, then I know that they are the same thing, so go ahead and return that. Else if comparing it is less than 0, right? Less than 0, that would mean that, actually, I guess the root is less than x, so therefore I need to go right, right? Go right, right? Else if this dot compare to is greater than 0, then I go left. Okay, there we go. Okay. What happens at the end if I don't find what I'm looking for? Yeah, return an unsuccessful search null. I've only done it for the root, by the way. Let's generalize this. Okay. So let's think about how we did it over here. I was keeping track of, implicitly, I was keeping track of a current node where I started out at the root, right? So let's establish a current node instead. I'll keep all that just for now, but we're going to modify it. So a tree node t current is equal to this dot root. Now when do I stop? When did we stop with this unsuccessful search, this 42? We went left, we went right, we went left, and at that point, what's the current node? Null. Right? So while the current node is not null, while the current node is not equal to null, right? Then what do I need to do? This right here. Compare it. If current, or this dot cmp dot compare, the current node, so current dot get element, and I'll compare that to x. If that's equal to 0, then stop. Return immediately. Return current dot get element. Right there. I'm just generalizing from the root over here. Else if, right? Bring that over here. Right? I compare the current node's element, so current instead of root, and x, and it returns something negative. That means that the current element comes before x, so I would need to go right. Right, so go right. I'm just verifying that. We wrote it before. Go right. And now, do I really need that else if? It's either equal, greater than, or strictly less than, so I go left. There. And I can get rid of all that. Right. How do I go left? Or go right, in this case? Current is equal to get right child. There we go. Current is equal to current dot get left child. I'm reasonably sure that this will work, but is there a way to test it yet? Because I haven't done what? I haven't added anything to it. Okay. All right. Let's come back to the drawing board over here and figure out how to add stuff. Implicitly here, we tried to search for 42. It didn't exist. If it had existed, where would it have been? As the left child of 45. Does that give us a hint as to how we can insert things? Insert 42. Well, if we insert it, it can't go into the right subtree because it would violate the binary search tree property. So we go to the left. Now we need to go to the right. Now we go to the left, and we always insert it as a leaf, right? As a new leaf. Right? So let's outline that. Okay. To insert, you start at the root, right? As you do with everything. You do a basic search, which is why we covered it first, until you, A, find the element, in which case no op, no operation, because you don't want duplicates in there, right? Maybe you do want duplicates, in which case, again, you have to break ties somehow, right? So you don't want duplicates, basically. Or B, find the space in which it would have existed, right? And you insert it as a new leaf at that location, okay? All right, so you could throw an exception to, you could be a no operation or whatever, right? And insert as a new leaf, right? As the new left or right child of the parent reference, right? Or the reference parent, okay? All right, let's try to codify that over here, all right? So what am I gonna do? I'm gonna basically do the exact same thing over here, except that I'm guaranteed, if I ever find it, by the way, then I return, right? Because no, I'm not gonna do it, it's a no operation. Otherwise, I break out of this loop, at which point I need to insert it. So let's try that. I'm just going to cut and paste this code up here and see what we have to modify. All right, so instead of returning, I will just return here. No operation. Already in the tree, return no op. Right? Okay. Otherwise, we get down here and we should insert it at the current node. Except that, how did we get here to begin with? Current ends up being null. That's all right, we can just go back to the parent, right? No, because it's null, right? We can't get its left child, we can't get its element, it's null. That's the end of the show. So ideas? I went too far, basically, right? I fell off the face of this tree. Right? I need to go one less iteration here, right? So when do I break out of this loop? I don't break out of it when the current is null. I break out of it when its child that should have that element is null. Right? Okay. Yeah. Somehow, right? I fell off this. I need to keep track of the parent that I just came from, right? So just keep track of two things, right? Current and what? Previous. Oh, previous, because we want the previous. Previous, right? What do we set it equal to initially? Well, null, because the parent of the current is null, right? Okay, that might be a corner case, actually, by the way. What happens when we need to insert into an initially empty tree? Think about whether or not what we're doing here is going to work, and then we'll come back to it, right? All right, otherwise, go left, go right. So you update the current, but before you do that, what you do? Previous gets updated to the current. Go left, go right, previous gets updated to the current. I suppose that you could have done that up here and avoided those two lines, but the repeated lines right there and right there. But I'm going to go ahead and keep those together. All right. So we should insert at the current node, but it's null. Null. So instead, we insert as the new child, a new child of previous. Because we broke out of this because current is null, right? All right, well, that just means that we need a new tree node. Tree node t new child is equal to new tree node containing x. We're inserting x, right? Yeah, there we go, x. Okay. And now we need to make the new child's parent previous. Right, so new child dot set parent to previous. Right? And then what do we do about setting previous dot set left child or set right child? Which one is it? Yeah, that's what we're going to have to do. Left or right? Left or right side? I don't know, but right. Return, just return here. Right. So which one? We just need to repeat this logic right here, right? So if we compare not the current, by the way, but the previous, right? And we get the element and that is less than x, then we may need to make it into its right child because we would have gone right. Else, we make it into the left child. Be good about your brackets. I don't want to see that. I always want to see brackets, period. Right?
Does it run without brackets?
Yeah, because one-liners bind to the if or else. But it's terrible, terrible practice. Because the second that you put in another line there, then it's wrong. Right? All right, so which one? The left or the right? Or the right or the left? All right, now do I have enough to test this? Yep. Let's go ahead and just get rid of all this. All right. Okay, binary search tree. And let's just go ahead and make it into integers so that it's easy. BST is equal to new binary search tree, right? Except that I need a comparator for integers. Integer dot, is there a comparator? You didn't give me a comparator, fine. I'll go ahead and create a comparator. What's the easiest way to create a comparator? CMP int is equal to comparator for integers, sorry, integer. I don't need to do that though, right? Comparator dot comparing, how do I do it? Integer, compare to. I think I can do it that way. Import that, and I think that that works. Int value. Is that it? Yeah, that'll work. There should be an easier way of doing this, though. So now that I've got this, I'll come back to this dot. Oh, natural order. There we go. Natural order. Okay. Nice. All right. Probably throws an exception if this is not comparable, right? In fact, let's read it. Returns a comparator that compares comparable objects in natural order. The return comparator is serializable, blah, blah, blah. It you should throw an exception, though, when comparing null. So let's take a look at the actual natural order comparator dot instance. Okay. Oh, I see. So it's the compiler checks for it. The compiler checks at compile time that what you're giving it integer is comparable. Otherwise, this would not work, right? This would not compile. In fact, I can show that to you. What if it was something uncomparable? Do we have something? Those are comparable. Tree node? There we go. Tree node elements of integer. There we go. That's definitely not comparable, and it's not compiling. Good job, Java. All right. Integer. All right. All right, so, and I will pass in CMP int. There we go. All right, now let's test it. bst.add 10. bst.add 20. Add 30. What would the structure of the tree look like if we did it in that order? Well, careful, we inserted it in that order. 10, 20, and 30. 10 on the top, because that ends up being the first one. 20 would end up being the right child of 10. And now when we insert 30, it's going to look like that. Right? So let's go ahead and see if it works. I mean, it's going to run, hopefully. Ah, good. Because previous is null. Remember what was that corner case I told you to think about and think if this would work? If it's initially empty. So let's take care of that. Because the root is going to end up being null. Right? The root ends up being null. You break out of this and then you try to insert it, but you can't because the previous is also null. Right? So one corner case here is if this dot root is equal to null, then what do? This dot root is equal to new tree node of elements of type T. I can leave it like that, of X. And that's it. And then, of course, return because you were done. Right? There. Now does it work? Well, it does at least run. Right? It ran now. Right? How do I know that it worked? bst.search for 10. Right? And system.out.println BST search. Right. Searching for 10 should result in 10. Searching for 20 should result in 20. Searching for 30 should result in 30. What else should I be testing? 40, something that returns null. 10, 20, 30, null. Right. How am I assured that that's the actual structure, though, and I just didn't get lucky or something? One way of doing that is to set a breakpoint and just do an ad hoc debugging testing here. Right. Switch over here and look at your binary search tree. There's your root, right? What's contained in your root? There is no left child, but there is a right child. What's contained in that right child? 20. Right? What was in the root, by the way, the element? It's going to be 10. All right, so the structure looks like it's checking out because there's no left child, but there is a right child containing 30. So you can use this to check out the structure of your tree if you were doing something quick and dirty. Right? The way that I would actually do it, though, is let's go ahead and stop. I think I've done it. Let's go ahead and take a look at the tree utils over here. Now that we've got binary search trees, oh, there's a large binary search tree, by the way. We'll do that later. That's this tree right here. I insert things in the proper order in order to produce this tree. Right? And then this is the one I was thinking of, though, with only 4 minutes yet left. Oh, ooh, what's the difference? 2 TXC. Oh, I know that this should actually be private, actually, because this one uses it. All right. All right, and then we're gonna darn it. We're gonna have to break encapsulation for this thing to work here. Let's go ahead and make this public. Right. So, TXC is an environment that you can use to in LaTeX to draw things. In fact, this is how this was drawn. Right. I generated LaTeX code and then compiled the LaTeX code, and it generates something that looks like this. So let's go ahead and take a look at it. It returns a string. So system.out.println bst.toTXC utils tree utils.toTXC of bst. There we go. And then I'm printing that out. There's the TXC code that produces this tree, right? And do I have an easy way of compiling this right now? You're using LaTeX in 235H, I assume, right? So what do you use? Overleaf. Good. Overleaf. Do I have? I think we can do it in 2 minutes. Log in with Google. Demo? I don't know what demo is. Let's find out what demo is. Hey, it's probably it's exactly this. I don't know what that is, but we'll go ahead and get rid of it. There we go. Oh, come on.
I think they changed.
I did. I erased it. Oh, and then don't erase document either. There we go. And TXC, fine, TXC, and TXC. Recompile. There we go. Yeah, we got it. All right. So all I did was write this recursive code, or did a pre-order traversal or something like that, or probably an in-order traversal, and it generated TXC code that the child node, we've got 10 here, which is a node. We've got a child node of 20 as its right child, a left child here that ends up being empty, just so that it looks nice, right? Otherwise, if we didn't have that, it would look like, if we didn't have all these empty children, we would have something that goes straight down, I think. Yeah, 10, 20, and 30, right? That's not a binary tree, right? 10, 20, and 30. Right. There. So that's how I use, visual debugging is also a tool at your disposal if you do something like this. Right. All right. Any questions? By the way, if you're interested in that I think that's in lab 15 that we provide code to do this, to generate a TXC diagram of this. All right. Otherwise, we'll continue there next time with deleting stuff and also testing some more stuff.